here's a question. If this was a capital C, how many joules would this be? 4,184, right? So they do that. Now, how come, real quick question, why do you think they don't just put kilocalories instead of capital C? Because it would scare people. And people are like, hey, what's this K mean? You know, and then, I mean, I gotta learn science to read a food label. So, yeah, that's basically what's going on. So, now in Europe, they might leave the kilo in there. Or in other countries where they use the metric system. But because here in the States we don't use the metric system as our normal number system, that might freak people out. Okay, so let's get to the first law. The first law, it's like Fight Club. What are the 3 rules of Fight Club? You don't talk about it, right? What's rule number 2? You don't talk about it. What's rule number 3? You don't talk about it. Well, in this case, in the first law, first law says you do talk about it. You talk about it all the time. One way of stating it is, and this is the official definition, energy can neither be created nor destroyed in any process. Okay, but usually when you say that to yourself, it's not going to register as having any meaning whatsoever. Another way of saying it is that the energy of the universe must be conserved. So what this basically says is that we cannot pull energy out of thin air. Okay, energy is always flowing, it's always moving from one place to another. Okay, but it's never being created out of thin air. Okay, it's kind of like money. You can't create money out of thin air. Oh no, wait, there's the Fed, never mind. Yeah, I always like to sneak that one in there. But really, ultimately, money actually really can be created out of thin air. Because ultimately, if you print too much money, you have massive inflation, and then the chickens come to roost, and you have situations like Venezuela and Argentina where they've got 50% inflation. So you can't do that forever. Hopefully we'll figure it out before it comes to roost for us. But just like money, energy is conserved. What else might be conserved? I always tell my wife time is conserved. Okay, because we're always talking about, well, how do you juggle this and that in terms of doing chores and such. So time is always conserved. You can't create time out of thin air. So there's lots of things in life that are conserved, and energy is one of them. And in a way, it's all tied together. Energy is conserved because time is conserved. If we had unlimited time, we wouldn't have to worry about energy so much. So energy is conserved. Another way of saying this, and this is my favorite, there is no free lunch. Okay. So it's like the soup Nazi from Seinfeld. You know, no soup for you. You know, no free lunch for you. Okay. So I'm going to ask you a question on the exam saying, hey, you know, like, list a couple different ways of saying the first law, right? And if you wrote on your exam, no lunch for you, Mr. Fernandez, I'd be like, all right. Get it. So, that'd be funny, actually. I would enjoy that. Okay, so, you had a question or? Oh. So the first law is manifested mathematically as well. So we have equations that express this conservation of energy. Okay. One way of looking at it is that we can say, well, the change in energy of the universe is equal to the change in energy, this delta sign means change. Change in energy of the system plus the change in energy of the surroundings must equal 0. So let's go back and look at this again mathematically. So delta energy universe has to be equal to 0 for energy to be conserved. Okay, we cannot have a minus or a positive change in energy for the universe because again we cannot create energy out of thin air. The universe as a whole, okay, is the energy and the system and the energy of the surroundings. So think of the system as a reaction, and then the surroundings as everything else around it. A lot of reactions create heat. All that stored energy with bonds is being converted into thermal energy. And then we might absorb some of that energy with our hands and get burned, for example. Has anyone ever suffered a burn before? Pretty much all of us at some point in time have suffered a burn. All right, you know, that's because the system is releasing heat, and our hand would be the surroundings, for example. Right? So the first law got you again. Okay, it's always there. So delta E, whether it's delta E universe or energy or system or surroundings, delta E is referred to as the internal energy. Okay, so one way of stating the first law, another way of stating it, would be this, mathematically. You could say, well, if I subtract the changing energy of the system over to the other side of this equation, I will now have a minus sign for my change. And so anytime you have a first law, okay, you're always going to have a plus sign on one side and a minus sign on the other. And that's probably going to be the hardest part about doing calculations for this chapter, is just remembering that. Remembering the first law. Right? Remembering that you have a minus sign on one side and a positive on the other. And that's just a consequence of the law of conservation of energy. Okay. You can also write this a second way. You can say, well, what if I want to just take the negative and put it on the other side? And I can do that as well. Okay. Doesn't matter which side the negative sign goes on, and it doesn't matter because the math will work out the same. So always remember, if you ever ask the question, what side does the negative go on? Does it matter? And I have students ask me this question a lot when it comes to thermochemistry. I always tell them it doesn't matter what side the negative sign goes on, as long as you have a negative sign somewhere, okay, on one side or the other. Okay. So again, how many ways can you state the first law? You can state it verbally, like on the last slide, or you can say it mathematically, like this. So ultimately, there's going to be several ways that you can tell me, okay, what is the first law, and mathematically you could pick either one of these. And there's other ways to describe it too, other ways to write it. So there are two main types of kinetic and, or two main types of energies, kinetic and potential. Internal energy is defined as the sum of all the kinetic and potential energies of all particles in a system. So if you think remember that thermochemistry is observed in bulk matter. So when we say it's the sum of all the kinetic and potential energies of all the particles in a system, well, when we see matter with our naked eye, we're seeing quadrillions and quadrillions of molecules coalesce together. Okay, each molecule has its own motion. Each molecule has its own kinetic energy. Each molecule, depending on its chemical makeup of the types of bonds in it, whether it's ionic bonds or covalent bonds, whether the covalent bonds are between sulfur and hydrogen or oxygen and hydrogen, different types of bonds have different energies, and because of that, they've got different potential energy. So, if you think about down to the molecular level and then ramping it up to the bulk level, internal energy, the definition of it makes sense. Okay, so think of quadrillions and quadrillions of molecules with their own motion, with their own type of bonds. Okay, and you can see how if you see a bulk piece of matter, the internal energy of that system is going to be the sum of all these kinetic and potential energies. The change in internal energy only depends on the amount of energy in a system at the beginning and at the end. Okay, in other words, we only care about the change in energy. We don't care about an absolute state of things. Okay, and the reason why is because, again, we're looking at bulk properties, and it's kind of hard to study one molecule individually when it comes to heat generated from that. So, such functions or such changes in internal energy, we can look at them in terms of state functions. So, internal energy is an example of a state function. We only care about the change. We don't care about the absolute potential energy. It's kind of like if you're going to meet up with a friend and you say, hey, friend, meet me at Fullerton College at 9 a.m. Okay, or your professor tells you, be here at 9 a.m. on a Saturday or on a Friday. Do I care how you got here? I don't, right? I just care that you got here. So do you care how you got here? Not really, right? You just care that you got from your residence to school, somehow you got here, right? And that's all you care about, right? And so the path in which you took to get to school today would be an example of a state function, right, for example. Okay, so that's an example of a state function. What is a state function? It's a mathematical function whose result only depends on the initial and final conditions, but not on the process used. what is a function? Like mathematically. So when I was in junior high, excuse me, not junior high, when I was in college as an undergrad, I would tutor we had a tutoring center at Cal State Fullerton, and I would tutor chemistry, but there was this guy there who was referred to as the math guy, because he was a math tutor and he kind of worked the desk there, but he knew everything there was to know about math. He was phenomenal when it came to math. And just talking with him was a joy, because I could almost feel the intelligence coming off of him as I talked to him. And so we called him the math guy. And he and I had this discussion at one point, and he was telling me that a lot of students don't appreciate what is a function, you know, and why are functions important? You know, he said, well, what is a function? Well, if I asked you, what is a function? What would you tell me? Right? It's like, well, I don't know, I'm just taking these math classes, it's numbers, and you know. What a function is you have an equation that for a given input value, you get an output value. Okay? What might be an example of an input and you get an output? Well, we've been doing graphs in Excel. You've got a mathematical function, y is equal to mx plus b, for example, right? That's the equation for a straight line. The input might be the x value, and the output would be the y value that you get from that, right? That would be an example of a function. It's not a state function, but it's an example of a function. So functions in general are important because they are used to predict behavior. You can use them to predict future outcomes that may not be predictable otherwise. So that's the power of a function. I just found this discussion that I had with them, I never thought about it, like, what is a function? And I had the same reaction that you had right now, like, what is one? I don't know, you know. But that's the way he explained it to me, and it's really stuck with me. So take it from the math god. Okay, and a state function is just the same, it's just that the function depends on the change in something, not in an absolute value input, but it's an input of a change in values. Okay, so that's what a state function is. Okay, and you can have many transfer steps in any process that involve many state functions for a given step within a larger process. Or the state function can describe, you know, a larger process, and again, it doesn't worry about the steps per se. Okay, so all we care about is that where we started, where we finished. State functions oftentimes, okay, have the delta sign in them. Okay, so if you see, for example, delta H, okay, remember delta H from Chem 107? Enthalpy, they call that reaction enthalpy. That's an example of a state function. Okay, I'll give you another example of a state function that you've dealt with in lab. When you're measuring volume in a burette, do you care about where you initially started versus where you finally ended? You don't really care about the initial and final readings. What you care about is the difference in those readings. So you could say the volume delivered by a burette is a state function. Okay, if I want to deliver 20 milliliters of liquid from a burette, I could start at 0 and end at 20, or I could start at 20 and end at 40. It doesn't matter where I started and where I finished, and as long as my change is what I wanted, right? So that's another example of a state function. So delta volume would be an example of a state function, for example. Okay. Something with delta in it is typically a state function. Here's another example of a state function. Have any of you climbed the mountains locally, like Mount Baldy? I used to go hiking at Baldy every now and then with my thesis advisor, who was a very avid hiker. Made me look bad on the mountainside, so I just never tried to keep up with him. He was a runner. And so Mount Baldy is about 10,000 feet, just over 10,000 feet above sea level, the summit, also called Mount San Antonio. It's like the mountain right here. You know, there's like a tall mountain like right here, and you look at it, it looks really tall. So that's 10,065 at the summit. The altitude climbed would be an example of a state function. Okay, you could take a more gradual path to get there, or you could take a more steep path to get there. okay? One path takes 12 miles, the other one takes 5 miles, but you're still having the same altitude change, right? So again, we don't care how we got there. You can also look at it as the energy to get there might be the same, right? How much energy do you think you're going to expel climbing up a steeper but shorter path versus a longer, more gradual path? In the end, energy is going to be conserved there, right? Because you got to hike longer, okay, versus hiking shorter but more brutally up there. I would rather take the gradual path just to pace myself, but ultimately it should still be the same amount of calories you're burning to get up to the top. Okay. So hopefully you have an idea of what a state function is and how it parlays into thermochem. So take chemical reactions as a system. Okay, chemical reactions are often used as a system, but sometimes also surroundings, but usually a system. So here's a system for you. Carbon reacts with oxygen and you get carbon dioxide. You're at a summer barbecue, you got the coal there, you know, at the park, you're roasting the steaks, you know, or chicken, whatever it is, and you're not thinking about chemistry, but understand that coal burning is a system and it's releasing heat out into the surroundings, including the food you want to cook, right? So that's thermochemistry at play there. So because the total amount of internal energy in 1 mole of carbon and oxygen is greater than the total internal energy in 1 mole of carbon dioxide, heat is released. Okay, so in other words, more heat is evolved when you're burning carbon and oxygen towards the right than it is towards the left. Okay, when we talk about bond energies later in the semester, I'll kind of get back to that. But this is clearly an exothermic reaction. So you remember the term exothermic maybe from Chem 107? If not, we'll get there too. So how can we write a first law equation describing both directions? All right, so here's coal burning oxygen, you get carbon dioxide, heat's released out. The surroundings might include your steak, they might include the metal grill, they might include your hand, hopefully not your hand, but maybe it happens. Okay, how do we write a first law equation for this? Okay, so I'll do the first one for you, and you can figure out maybe the second one. So here's the first one. You can say, okay, delta energy, change in internal energy for the reaction, which is this, equals a positive change in energy for the surroundings. So the negative is on this side because heat is being lost from this system and it's being gained by the surroundings. Okay, so that's why it's positive on this side. All right, when we say positive, though, sometimes they just don't write the positive, so they'll just leave it as itself. What do you think? How do you think this equation would change for this scenario? And not much of a difference, but there is one change. Minus would be the other side, right? All right. Now, let me tell you something. If you figure out a way to efficiently do this, to convert carbon dioxide back into usable carbon and oxygen gas, you let me know, because you're going to be a very wealthy person, and I might want to like borrow some money from you, i.e., an interest-free loan that you never pay back. Okay, so if you figure out how to do this, you let me know. So it's very, very difficult, extraordinarily difficult, extraordinarily energy inefficient to go backwards. Right? This is why once you pump carbon dioxide in the atmosphere, you can't go back. Right? It's because of the first law. It's because of thermodynamics. Okay. So, but if you could do this, if you could put energy back in, okay, to do this, you know, it would take a lot of energy from the surroundings to do that. If you think about carbon dioxide, think about the molecule. CO2, do you remember the Lewis structure of CO2, going back to 107? Carbon in the middle with 2 double bonds to each oxygen, do you remember that? Okay, in order to put this back into these, you'd have to break those double bonds. All right, that takes a lot of energy. All right, and that's why in this scenario, it's not very feasible. Okay. So we can observe energy exchange through heat and work. Heat and work are not state functions. Okay, they are. It does matter how the heat is evolved, right? How the work is done. So heat is given by the letter Q. You might remember the equation in your Chem 107, Q is equal to MCAT. So you'll see that here. Okay, Q is equal to heat, W is equal to work. If you combine the two to measure internal energy change, okay, it's Q plus W. All right, like I said before, Q and W are not state functions. Their value does depend on the process. Okay, so here's an example. Determine the change in internal energy of a system that does 96 kilojoules of work and absorbs 32 kilojoules of heat. So with thermochemistry problems, what you'll find is that the words matter. So let's just read the sentence again. It says, determine the change in internal energy of a system that does 96 kilojoules of work and absorbs 32 kilojoules of heat. Okay, so if you do work, if I said, yeah, he does work, is he losing energy or gaining energy? He's losing. So that means that there's going to be a negative sign there associated with that 96 kilojoules. And then if you absorb heat, okay, do you think, if you absorb heat, do you think you'd be gaining or losing heat? Be gaining. Sorry, gaining means it's a positive, right? So what do you think the internal change in energy would be? So let's see. So delta E is equal to Q plus W. All right, Q in this case is positive or negative 96?
Negative.
Yeah, it's negative 96, but the work, excuse me, the heat, not the work. I got this backwards. So heat was 32, right? And then the work was negative 96. Okay, so the overall energy change, the overall internal energy change, what do you think that's going to be? Well, just do a little bit of some basic arithmetic. So it's going to be negative 64. So you see how the words do kind of take apart, right? So does means negative, absorbs means positive. All right, try this one on your own, see what you get. So what answer did you get? So negative, no wait. Well, let's see. If you have 148 kilojoules of work done on it, is 148 going to be positive or negative? Positive, right? Yeah. So work is going to be positive. What about the heat? Gives off.
Negative.
That means negative, right? So minus. So that comes out to be overall 97. If I'm doing math right here. Should be 97. No, I'm not doing it right. Oh, wait. Perfect, all right. I'm thinking like, I was thinking below 3 anyway, all right. Yeah, 103. All right, so any questions on internal energy change so far? All right, so delta E is equal to Q plus W. It's basically, the main equation we've been working with. Q and W themselves also have their own equations built into that. So heat is the flow of energy caused by a difference in temperature. Okay, and that's generally speaking given by Q is equal to cat. Okay, where C is the specific heat or the heat capacity of the system. But the one that we'll probably be using maybe a little more often, but we'll still use this one as well. The energy required to heat an amount in grams of a substance is given by MCAT, right? And this is the one that you're more familiar with. So M is the mass of the system. Specific heat is that of the particular substance that you have, and then delta T in Celsius. All right, so Q is equal to MCAT can be used for the heat. Here's an example problem of that. A 300 gram sample of water is heated to 62.0 degrees centigrade after it absorbs 56 thirds of heat. What is the initial temperature? All right. So what equation do we use? That's always the hardest part, right? Which equation do we use? So we've got like grams of a sample of water, right? So do we use CAT or MCAT? And we use MCAT. There will be a time when we use the other one, but that'll be for calorimetry. So you have MCAT. Q is equal to M CS, specific heat. And it's asking us, it's giving us, let's see, it's giving us a temperature, and it says, what is the initial temperature? So if you have Q is equal to MCAT, what can delta T be written as right here? Yes, right, so T final minus T initial, that's our little more expanded MCAT equation. So it's giving us 300 grams. We know that the specific heat of water is, actually just give that to us here. Do you remember what the specific heat is of water? 4.184 joules per gram per degree C. It's the same number as when you're converting calories to joules, right? That's the benchmark. Okay, and then the final temp is given to us, it's 62. So how do we solve this equation for Ti? And this requires a little bit of math, okay? So if we divide both sides by MCS, okay, now we have T final minus T initial. All right, we have that situation now. Okay, how do we solve for Ti then? How do we isolate that? We can maybe add Ti to both sides. Okay. And now from there we can get Ti is equal to Tf minus Q over MCS. Are you down with the algebra? Right, so first divide both sides by the MCS, get rid of the factor there. Then we have T final minus T initial. We added T initial to both sides to get this over here. And then we subtract out the Q over MCS over to this side. That's how we got there. Let's plug in the numbers. All right, so we have 62